welcome to this special episode of Frequency Matters, the RF Microwave Update series. I'm Pat Hindle, and today I'm talking with Sid Devarajan, and he is Managing Director of High-Speed Converter Technology at Analog Devices. Welcome, Sid.
Hi, Patrick. Nice to be with you.
So there's been a lot of emphasis on moving the computing to the edge of the network, and that reduces latency and bandwidth needs. And you've talked about high-speed converters as the anchor for RF applications at the intelligent edge. So exactly what do you mean by, high-speed converters being this anchor for RF applications at the intelligent edge?
Yeah, that's a very good question. And let me start with what we mean by the intelligent edge, because it's sometimes misunderstood. Traditionally, signal processing happened at a centralized location, like it could be a data center, a ground station, or a central office. The intelligent edge is the paradigm shift where sensing, processing, and decision-making happen right where the data is created, at the antenna, at the sensor, at the radio head. It's the convergence of high-performance analog and digital processing, and increasingly AI, all pushed out to the physical point of interaction with the real world, which is analog in nature. Within that intelligent edge, the high-speed data converter, the ADC on the receive side and the DAC on the transmit side, is the single component that most fundamentally determines system-level performance. It sets the noise floor, the dynamic range, and the usable bandwidth. Every other component around it is designed to optimize the signal presented to or generated by the high-speed data converter. And here's the critical point. The entire signal chain is architecturally built around the data converter. The front-end RF signal conditioning, LNAs, VGAs, filters, they're designed to present the optimal signal to the data converter's input or process the optimal signal out of the data converter. The gigahertz class clocking subsystems exist to provide pristine sampling clock that the converter demands. And the downstream digital processing, channelization, filtering, frequency planning is designed to extract what the converter captures. The high-speed converter is both the performance bottleneck and the architectural center of gravity of these systems. And increasingly, we're moving to direct RF sampling systems. And I'll tell you a little bit about what this is and why it's so transformative. By digitizing the RF signal directly without intermediate mixing stages, you eliminate mixers, local oscillators, IF filters, and dramatically simplify the entire signal chain and the hardware needed. More importantly, the system becomes completely software defined. Channel selection, filtering, frequency tuning, all of that happen in the digital domain and are reconfigurable now with software. That's a game changer, whether you're designing an O-RAN system, a phased array, or a communication tester.
Yeah, the high-speed converter technology really has advanced, making all this possible. What are the key high-speed converter specifications that system designers should focus on?
Yeah, traditionally, engineers evaluated high-speed data converters with simplistic SNR or ENOB type metrics. Those still matter, but for modern RF sampling applications, they can be somewhat misleading because they integrate the noise over the full Nyquist bandwidth, which is not how converters are actually used in the end application or in the system. So I'll go through a few important metrics based on how they're actually used in the end system. And the first and most important one is the noise spectral density. That's the converter's noise per unit bandwidth measured in dBFS per hertz, and it sets your receiver's sensitivity. The lower the NSD, the smaller the signal you can detect in a given channel bandwidth. The other one is in-band SFDR, including intermodulation, distortion, third order, fifth order, the ones that fall in band. And I want to be precise here. When you talk about SFDR, in-band SFDR is very important because in almost all these systems, what you care about is what is the spurious content within my bandwidth of interest. And ideally, you want all other spurious content to be lower than the third order intermodulation distortion. And you want that to kind of dominate because that's somewhat fundamental and behaves in a predictable way. So that's what determines whether you can detect a small signal in the presence of a large interferer. The next one is clock jitter and phase noise. So in a direct RF sampling system, the sampling clock is effectively your local oscillator. And so jitter degrades the signal to noise ratio, and the penalty grows as you want to capture higher and higher frequencies or synthesize higher and higher frequencies on the D2A converter side. At multi-gigahertz, you require sub-100 femtosecond types of jitter to achieve today's performance requirements. And so the phase noise of the clock and the jitter directly translates to kind of the noise in the spectrum and the phase noise of the final digitized signal or the synthesized signal, which impacts things like in a radar system, the Doppler processing, in a communication system, the EVM. And so the clocking solution cannot be an afterthought. It is important to design it, co-design it with the converter to meet the full performance of the converter. And the last very important metric these days with massive arrays in many systems, massive MIMO, phased array systems, is power dissipation. As systems scale from tens of data converters to hundreds and maybe even thousands of high-speed data converters in these systems, power thermal constraints impact cost and performance of the system. And so creating gigahertz data converters at lower and lower power dissipation to meet the demands of the end system while not sacrificing both the performance as well as the bandwidth is the big challenge in front of us today in high-speed data converters.
And what applications are being the most transformed by these advances in the high-speed converter technology?
Yeah, the common thread is the move towards wideband software-defined architectures, and the high-speed converter is the enabler in almost every case here. So one example is phased arrays. The transition to every element digital beamforming puts the high-speed converter behind every antenna element. As channels combine, array gain coherently improves system dynamic range. So the per element converter needs sufficient dynamic range to leverage that array gain that you get from the system and does not have to by itself meet the full system spec. However, power dissipation needs to be very low. So ultra low power while still processing gigahertz of bandwidth become very important in phased arrays. A similar trend in 5G, O-RAN, and 6G, where the high-speed converter-based transceivers are enabling software-defined radios and can process not just one band, but multi-band and pretty much any band digitally all together within one receiver or with one transmitter, which is exactly the type of flexibility that O-RAN demands. And as the industry looks towards 6G, there are new FR3 bands that are emerging, which go from 7 to 15 gigahertz, which now, to make that new band software defined, requires the high-speed data converter to operate that much faster and process those signals all together so that we can, in a software-defined way, select which bands are of interest for a given radio. In instrumentation, things like instruments like oscilloscopes, spectrum analyzers, comms testers, in many ways, the data converter is the instrument. That's where you're digitizing real-world signals of interest. And so they put a lot of onus on both the performance as well as the bandwidth of these data converters to make them fully software-defined. One thing interesting with instrumentation is that the instruments are used to measure, phased array, communication standards. And so typically the data converter in these instruments have to be ready ahead of the standards and have to have performance greater than what the standard demands in order to be able to measure the standard. And so instrumentation in many ways pushes the envelope of performance of high-speed data converters. And then the last one I would say is in spectrum monitoring. Bandwidth is everything. You want to be able to see as much of the spectrum instantaneously as physically possible. And so high-speed converters with multi-gigahertz, even tens of gigahertz instantaneous bandwidth open up situational awareness capabilities that weren't possible in previous generations of technology.
Yeah, it improves things on a lot of fronts. And so the high-speed data converter doesn't operate in isolation. How does the surrounding signal chain factor in?
Exactly right. Realizing the converter's full performance requires an optimized system in 4 dimensions. One is the RF front end or the RF signal conditioning that comes after the D2A converter and before the A to D converter. So things like high performance LNAs, VGAs, output amplifiers, and filters that preserve signal integrity between the antenna and the converter are very important. And ADI has a very broad portfolio of what we call RF attach, RF components that work with our data converters to realize the required performance. Because if the RF signal chain doesn't meet the performance, you cannot recover it with the data converter. Similarly, on the clocking, I talked about needing sub 100 femtosecond type jitter as well as very low phase noise. And so the clocking solutions, the low jitter PLLs, the ultra low phase noise in the entire clock distribution are all important to meet system requirements. So that's kind of the second vector. The third one is, data converters require typically multiple supply domains in order to reach the maximum performance. The analog domain needs to be kept pristine from the digital, so there's no coupling that degrades the high-speed data converter's performance. And the high-speed data converters is where the analog world meets the digital world, and the digital world fundamentally creates a lot of noise. And so things like our silent switcher regulators and ultra low noise LDOs are critical to deliver the quiet power supply and ease of use for the end system, so that you can plug in the required power management from analog devices and you can power these data converters with the best performance. So that's kind of the third vector. And the fourth vector is the digital feature set. The data converter either produces a lot of data on the A to D side or takes in a lot of digital data and then synthesizes the analog signal. And so here's where I would highlight analog devices is Apollo MXFE or 809084, which we will be featuring prominently at this year's IMS. And so you're welcome to come and visit our booth there. And the 809084 integrates industry-leading 20 plus gigasample per second multi-channel high-speed ADCs and DACs with a rich array of digital processing right at the edge. So things like digital down converters, digital up converters, NCOs, programmable FIR filters, fast frequency hopping, and system diagnostics like loopback modes and spectrum sniffers are all integrated right there at the edge. And this on-chip processing delivers three key system benefits. It enables low latency systems. It lowers system cost and power because the digital processing happens right there at the edge with hardened digital logic that's optimized for low power dissipation and low cost. And so when you combine the benefits of the lower power, the lower cost, and the ability to be right at the edge and lower latency, it becomes an extremely powerful digital integration with the data converters. So the combination of RF, clocking, power, and digital processing are key to round up the signal chain and make this entire high-speed data converter, where the high-speed data converter is the anchor, but you got to build around the anchor to make the end system.
And so looking ahead, where is the high-speed converter technology heading?
Yeah, so that's a great question, and we all like to have the crystal ball and think ahead because developing these high-speed data converters takes a while, and so we want to anticipate where the market's moving and be ready for our end customers and for the industry in general when higher performance is needed. So the first one would be, I would say, continued improvements in performance. And the performance is basically a handful of vectors. It's bandwidth, higher sample rates for ease of use, and software-defined radios, lower power for massive arrays, and higher dynamic range because that fundamentally sets what type of signal you can synthesize or quantize. And so continuing to push that envelope of the data converter, I think, will continue to be an important dimension of advancement. But the second very important one that's in some ways not obvious when you talk about a data converter, but is very important is system-aware high-speed converter architectures. The high-speed data converter's architecture fundamentally determines some properties of the system. So converters are not just designed for their datasheet spec, but to simplify the system around them. So three examples, Analog Devices has unique randomization technology for our interleaved high-speed converters, which spreads residual interleaving spurs, the spurious content, across the entire spectrum rather than concentrating them at discrete frequencies, which makes the entire radio more usable over a wide bandwidth, making it a software-defined receiver. The second is continuous time ADC architectures that Analog Devices have inherent anti-alias filtering. The benefit of that is it eliminates the need for expensive filters, or at least lowers them substantially, saving system cost and power. The last is, I'll talk about is that the industry-leading RF DAC linearity. So having industry-leading linearity means that the filtering that's required at the output of the DAC can be relaxed again, saving system cost and power. And so you want to build these data converters with very much a system mindset on what aspects of the architecture can make the system easier to use, lower the cost, lower the power dissipation and the barrier for making that system work. Kind of the last and third aspect of high-speed converters in the future would be making it a system-level platform. And what I mean by that is completely software, more and more software configurable. People want to buy one system and just with software be able to use it in a wide variety of end applications. And so things like self-calibrating data converters that can recalibrate and reconfigure for various bands of interest. Integrated digital signal processing like we have in the 8094 I talked about, but continuing to enhance, add more, make it lower power, more optimized for various systems, and adding in system features based on knowledge of the end application. Another trend related to this system-level platform aspect of high-speed data converters is going to chiplet-based architectures. Because what chiplet-based architectures do is allow us to optimize an analog data converter chiplet with digital processing or beamforming chiplets through advanced packaging, delivering the best analog performance on the data converter side at the right process technology, along with the best digital density on the leading edge process nodes. So for system designers, this means fewer components, faster design cycles, and the ability to upgrade capability through software. That's the essence of, I would say, the intelligent edge. And so the high-speed data converter is right in the center of it.
Well, that's some very forward-looking techniques there. I look forward to that. So thanks, Sid, for talking with me today about high-speed data converters as the anchor for RF applications at the intelligent edge. It's been very interesting to learn about this, especially as an RF guy. We're not as familiar with these. So to our audience, you can find more videos at videos.microwavejournal.com. Thanks for watching.